Hello, everyone. Welcome back to the AAS YouTube channel. And this is the good stuff. This is the AAS Journal Author Series. And I'm super happy to have Adam Jermyn with us today. Hey, Adam.
Hey, Frank. How are you doing?
Good. What is your geolocation?
So I'm currently in Western Massachusetts near Springfield.
Okay.
But normally I'm in New York in the normal times.
Oh, in the Flatiron? You're a Flatiron?
Yeah.
Very cool. Very good. Let's see what you got. You got a telescope there over your left shoulder, looks like. What is that?
Yeah. I don't remember. It's I only just moved. I moved back in here, and so it's been sitting there since I was 10 or something.
Okay, very good. So you're not looking for magnetic fields with early type stars with that telescope, are you?
No, if only.
Okay, very good. Cool. So Adam, what do you like to do for research?
Yeah, I like to think about stars mostly, and sort of within that, stellar evolution, some of the microphysics. Lately, I've been thinking a bit about equations of state, and also more macrophysics, turbulence, and what transport processes are going on. So sort of fairly broadly, things involving stars. If a planet looks like a star, gas giants are fair game, I think.
Yeah. Very cool. Very cool. And that will lead us to this really lovely paper, everyone, which is, let me do the screen share. And this is the origin of the bimodal distribution of magnetic fields in early type stars. Adam, take us away.
Okay. So I guess just to sort of give the context, there are these observations that suggest that, as the title said, there's a bimodal field distribution. So there's a sort of population of stars, of early type stars, that are very strongly magnetized. At the low mass end, sort of those are the AP-BP stars, and those are a few hundred Gauss up to 2,000 Gauss. At the high mass end, you get those stars that are up to, say, 10 kilogauss, 20 kilogauss.
Okay.
So there's one population that's seen really strongly magnetized. And then there's a population that has very weak fields. So among the A and B stars, those tend to be sort of 1 Gauss. And for a while, this was not even sort of a measured population. It was just lots of null detections of fields in lots of these objects. And so the question that got us started here is just, why are there these two populations?
Yeah.
In particular, why is there nothing in between?
Okay. So sort of
yeah. So so I think we mentioned this on the first page here, but yeah. So it's this Cantiello and Braithwaite 2019 reference, just in the second paragraph. So we sort of have, I think, an order of magnitude handle, at least, on the field strengths that we get at the low field end, right? So one of the things that this is Matteo Cantiello and John Braithwaite did in that paper, is they calculated the equilibrium dynamo field that you would expect from the very thin helium ionization layers that you get near the surfaces of these stars. So these ionization zones are convective, very weakly convective. And so they worked out what the dynamo saturation field is, what that would look like at the surface. And you come up with sort of Vorter Gauss, at least at the A and B. So it seems like there's a reasonable explanation for those weak field ones. Right, you have these near surface convection layers, they build a dynamo, and that then pushes your field up to the Gauss. So then the question is, where are these really high field ones coming from?
Okay. Given that, maybe larger convection zones?
Yeah, so I mean, that's certainly one possibility. Another is, as you spin up your star, your convection zone generates a stronger field, we think. So maybe it's rotation, although it seems really hard to explain just by rotation. So I guess So that's really the first piece of physics we put in, is just this, if you have one of these zones, you get a dynamo, that dynamo builds a field. There are really only two major pieces of physics in this paper, and the other one comes in around equation, let's say equation 1.
Okay. Looks like a stability. Yep.
Yeah. So the thing about these convection zones, right, is that I think it was Zeldovich who first suggested this, but we think that convection zones want the fields to be sort of around an equipartition. So if you start with a field that's weaker than equipartition, you have a dynamo, it builds it up. But if you start with one that's stronger than equipartition, you bring it down.
Okay.
So this happens. There's a schematic actually. I promise we'll come back to figure 1, but there's a schematic around figure 8.
Let's take a look. Oh, yep. There we go.
Yeah, so what we think is happening is when you have a stronger than equipartition field, the convection zone sort of generates lots of reconnection events. And it generates these reconnection events faster than it amplifies the field. Right, because if it didn't, then that wouldn't be the equilibrium strength.
Right.
And over time, we think sort of order, hundreds of turnover times, these reconnection events are going to weaken the field down to sit at equipartition. So that's the, so if you just take that part of the story, then it's really hard to understand how you can still have these strong field populations.
Mm-hmm.
Right, because if you imagine starting off with some initial distribution of fossil fields, it's really difficult to see how you end with a strong field if the convection zone really does just eliminate all the strong field ones. And so that's actually the lead into equation 1. Even though the order of the paper may not suggest it.
It's okay, all good. Okay. So what is the, if you started with some fossil field, which is sort of an order of magnitude estimate on the time scale to reach equilibrium?
So turnover times in these convection zones are days.
Okay.
So if you have turnover time, so a couple of years.
Right.
So if this is happening, you essentially should never observe these strong fields.
Correct. That's what I'm getting at. Okay.
Yeah. Yeah, that's a good point. Okay, so this got us thinking. Well, that sort of rules out having convection in the strong field stars, right? Because if there's a convection zone, then we shouldn't have strong field stars. And so it turns out there's been some work on this showing that if your magnetic field is above a critical value, in particular, if the vertical or radial field strength is above the critical value, then you don't get convection at all. So this comes out of the linear stability analysis that just shows that the normal convective instability goes away above some critical field strength. Yeah, so equations 1 through 8 is just us rearranging the criterion in equation 1 to turn it into a critical field strength.
Yes.
And if you want to just get the order of magnitude here, it's the point where B squared for the magnetic pressure is of order the gas pressure.
Mm-hmm.
So that's sort of the characteristic scale. And that was actually an argument that was made in this McDonald and Petit 2019 paper that we referenced for the original criterion. So they were pointing out that there's an O star that has a magnetic field where the magnetic pressure exceeds the gas pressure in the region where it ought to be convective. And they noticed that that star also has no surface turbulence.
Okay.
So they took macro turbulence measurements,
Mm-hmm.
and they see no macro turbulence in that star. And so that's maybe a hint that there is actually a connection.
Interesting. Okay.
Okay. So if you believe that, then the story becomes, well, you had some broad distribution, and I think this is figure 9. you imagine that you start with some broad distribution of fossil field strengths, which is the top panel. Yeah, right there. And then, so if they're weaker than the dynamo equipartition, they get amplified just by the convective dynamo. If they're stronger than the dynamo, but weaker than critical, then you still have that convection zone, and you're going to erase the field. You're going to bring it back down to the dynamo field.
Yes.
And then if you're above the critical field, you turn off the convection, or rather the convection never gets started.
Yes.
And so you preserve that field. The fossil field just gets locked in.
Okay.
And so we think that what's probably happening here is that sort of all of the weak field ones are dynamos, and all of the strong field ones are preserved fossil fields that just never went away.
Okay. All right.
Okay. So then we just need to be sort of quantitative about this. So figure 3 is where we start getting numbers.
Figure 3.
Yeah, for anyone who wants to read the paper, we start out by sort of giving the physics and then we construct the story. But that's maybe not the most natural way to go through it. Yeah.
Okay.
Okay. So this is for a 2.4 solar mass model sitting on the main sequence. And the horizontal is log of temperature. And then if we look in the upper panel, that's log of magnetic field and gas. Okay, so there are 3 convection zones labeled. There's a thin surface hydrogen layer, which is on the right. Then there's a thin helium-1 layer. And then there's a slightly thicker helium-2 layer. And so the blue lines in each case are the dynamo equipartition field.
Okay.
So this is, you set the kinetic energy equal to magnetic energy.
These are the low ones.
Yep. The pink lines are the same thing, but with some rotation, a rotation rate of 150 kilometers a second.
Okay.
So that's just, we wanted to show that rotation makes a difference, and that maybe explains some of the dispersion in the dynamo fields. Okay. And then the green lines are the critical field. So this is the critical field needed to shut off convection at each point.
Okay.
So the thing that we think of as the critical field overall is the highest point across all the green lines. Because if you leave any of the, if you picked a field that was, say, 10 Gauss, that would be enough to shut off some of the helium-1 and some of the hydrogen layer, but definitely not enough to shut off the helium-2 and not enough to shut off all of the helium-1 and hydrogen. And so presumably those convection zones would still act, maybe they're a little smaller, but they'll eventually bring down the field everywhere, at least in the surface. And so for thinking about this, we're pretty sure that the critical field has to be, or the critical field that you care about for this has to be the highest one that you get.
Okay, let me ask you a question.
Yeah.
The difference between the blue and the pink was rotation. So can I just keep rotating the star faster to get it up to here?
No. I mean, you can spin it a little faster, but 150 kilometers a second is already pretty fast.
Yes.
So you'll hit breakup long before you get to the green line.
Okay, very good.
In fact, you can show the green line is more and the equipartition field you would get for sonic convection.
That's interesting. Okay.
And that's just the statement that, for an ideal gas, the pressure goes like rho CS squared. And so if your convection is sonic, then equipartition, your energy goes like rho CS squared. In fact, I guess we don't show it, but you can see that the critical field does relate to the convection speed, because the orange line in the bottom panel is showing you the convection speed. So stronger critical field corresponds with the stronger convection zones.
Yep. Okay, I'm with you.
Okay. So then if we just slide on over to figure 2, now figure 2 will hopefully we can explain what's in it. So this is sort of a magnetic HR diagram. So log L on the vertical, log T on the horizontal, and of course flipped as normal. The coloring is log of the maximum critical field anywhere in the model. So that's sort of the peak of all the green lines. Take the biggest one. That's the thing we plot from figure 3.
Oh yeah.
Right.
Yeah. Mm-hmm.
Right. And then we have a grid of the models, and so we're doing some interpolation just to get color map. And you can see some of the text that we used in this grid overlaid, and those red dots just represent fractions of the main sequence lifetime. So it's sort of quintiles of the main sequence.
Okay, got it.
So that's just to give you an idea of how the field evolves over the main sequence.
Yes. Okay. Okay.
So 2 things I want to note here. One is at the low mass end, the field gets higher. Right, so purple is stronger field, and so that's about a kilogauss.
Yes.
And then as you go up in mass, the critical field goes down. This is just telling you how the different ionization zones are shifting as you change T effective. To first approximation, that's all you're seeing. But what that means is that if you see a 2 solar mass star with a strong field, chances of, at least our prediction would be that field is kilogauss or higher.
Mm-hmm.
And in order to see weaker fields that are still super equipartition, you end up needing to go to higher masses.
Yes.
Okay. But ballpark, so we started off with this story, and then we just went and made this figure. And we were pretty happy that, this is the right order of magnitude, at least. It's sort of a few hundred to 1,000 Gauss, depending on what mass you look at. And that's around where you start seeing the PPP stars. Okay. Now, if you go, let's see. The next place to look is probably figure 5. So the story for O stars looks pretty different. I mean, the broad story is the same, but the details are a bit different. So for the O stars, right, you get this iron convection zone.
Yes. Mm-hmm.
And the iron convection zone is much stronger than the helium ones that you get at lower masses. And so you can see it's actually almost sonic. The convection is going at a few by 10 to the 5 centimeters per second, which is close to the sound speed. Yep. I saw you going up to the critical field there. Yeah, that corresponds to equipartition being near critical. So this predicts that the gap between the equipartition, the sort of the lower mode of the field distribution, and the high mode should be closer. Like those two should be closer together as you go to higher masses, because the equipartition field is getting stronger relative to the critical one.
Right. Okay. Okay. Cool.
Okay. So a lot of I guess lacking an observation of a star that starts off, with a really nice strong fossil field and then suddenly loses it. A lot of the way that we try to connect this to observations is by looking at trends like that and seeing whether or not we see them, or whether or not people have seen them. So I don't actually know if that one's been seen, but that would be one to look for.
Okay, cool.
Um, uh, and maybe just another way to see that is in which figure that we show this in. Figure 1. So figure 1 is more or less a zoomed out version of figure 2.
Mm-hmm.
That includes up to much higher masses.
Yes.
Note that the color scale is different here. I mean, it goes the same way. Purple is higher field, but it's just a different numeric scale.
Okay.
So what you see is right around 7 solar masses, there's this big ridge.
Yeah.
And that ridge that cuts right across is onset of iron convection. That's the iron bump.
Gotcha. Okay, cool.
So a fun prediction here is imagine that you start off with, say, our 6 solar mass model.
Mm.
And let's say that your field is 1,000 Gauss, your fossil field on that star is 1,000 Gauss. Okay, so you're nice and supercritical. So you don't have any surface convection. And then you evolve. And at some point you heat up and you cross over and you get iron bump convection, and then you're suddenly subcritical. And so what we would predict is that these, say, 6 solar mass stars, if they start out with a field of a kilogauss, they ought to lose it by the time they finish evolving on the main sequence. Right, by the end of the main sequence, they should be gone.
Cool. Yes. Mm-hmm.
So that one, we don't have specific evidence of that exact example, but there are trends that point in that direction. So the observed fraction of magnetic O stars goes down with age on the main sequence.
Okay. All right.
And because you have to use you have to use a lot more telescope time to do the measurements that detect the lower mode. When you read these papers, oftentimes magnetic fraction is really code for the higher mode, right? It's really telling you about the strong fossil fields, because all of these have some magnetic field. So at least that trend seems to work. Trends in terms of like total flux measured also run that direction. So you see sort of averaged over a population, total magnetic flux tends to go down as the O stars age.
Okay.
And there's no, as far as I'm aware, there's no such observation for the lower mass end. So like the 2 to 4s don't, I think, show much evolution there.
Okay.
Yeah, so that's the main story.
Very cool.
Yeah, I think the thing I'm most excited about here is actually the correlation with macro turbulence, right? Because if it turns out that the magnetic field is shutting off these convection zones, and if it turns out that macro turbulence is due to near surface convection, which a few people have proposed, then a very direct prediction is that the supercritical ones should have no macro turbulence.
Yes. Yes.
And we've seen in section 5.4, we list all of the objects we could track down that we're confident have supercritical fields and have attempted measurements of macro turbulence.
Mm-hmm. Babcock star.
Yeah, I mean, so I find that one kind of hard to imagine, right? It's 70 kilogauss is sort of a wild number there. Wow. Yeah. So we have like 1, 2, 3. There are four or five objects here.
Mm-hmm. They
all have weak or consistent with 0 macro turbulence. And they all have definitely supercritical fields. So these are, I think, the best candidates. But if someone wanted to go and look for this trend in others, I'd be excited about that.
Well, the prediction's pretty clean. Maybe motivate some of the observers who are listening in to go for it.
Yeah.
So cool. So maybe that'll lead us to, unless there's something more you want to say, maybe this will lead us to sort of future directions on where the field goes here. Maybe some of the observers will want to pick this up and run with it. Are there other calculations that may be in the pipeline, either 1D or multi-D, or are there new instruments coming online? So just sort of where do we go from here over the next 5 years to verify this prediction?
Right. So I think one pretty clear place to go is to try to, at least if you assume that this is right, this gives you a way to infer the distribution of fossil fields.
Okay.
Right, because you can, if you can take a population of stars where you have measured field strengths, toss away all the ones that have really weak fields where we don't think it's a fossil field. And then if you can also infer with your favorite isochrone code what the how far along it is on the main sequence.
Okay.
I think this gives you all the pieces you need to go and back out at least sort of the tail end of what the fossil field distribution looks like.
Okay.
So as far as I'm aware, that's not something that's been done, and I think would be really a good thing to do. I guess 3D MHD simulations of convection near the surfaces would be nice to verify that you indeed can erase strong fossil fields.
Yes. There's certainly a whole community of people who do the sun, for example, or in some cases larger stars, more massive stars. So this might make an interesting project, right? Just dial up the field for your given simulation and see what happens with the outermost convection zones.
Yeah. I think I can't remember at the moment who, but I think there have been a few papers recently that maybe weren't quite in the right parameter range for this, but that were attempting the same experiment in spirit, sort of threading a strong field that was super equipartition and subcritical and seeing what happens.
Yeah, I don't want to put everybody on the spot here, but yes, know what you're talking about. Yep, very cool. All right, so the future is it's not a solved problem. There's some interesting directions to pursue over the next 5 years or so, and gives the community some nice targets to go after on fossil fields in early type stars. Very cool.
Yeah. Maybe just add one quick thing. A great way to falsify this that I think would be pretty direct would be if you saw objects with subcritical super equipartition fields. I think that would pretty much destroy the story here. And you would only have to look at the object for about a year to rule out that it had only just switched. Although I think having caught one like that is already very unlikely. So I think if you see one of those, let me know. Those are that would be great evidence against that.
Yep. Well, falsifiability is of course a key component, at least of some theories. That is awesome. Okay, that'll do. Thank you everyone for tuning in, and we will see you on the next one. Thank you, Adam.
Yeah. Thank you, Frank.